Góðan dag og verið velkomin á þennan fyrirlestur sem að haldinn í sameiningu af Fleti, félagi stærðfræðikennara og Rannsóknarstofu stærðfræðimenntun hér á Menntavísindasviði. Einn af grunnþáttunum í nýju aðalnámskrá grunnskóla lýðræði og mannréttindi og margir sjá nú ekki neitt samband á milli stærðfræði og mannréttinda, en Barbara ætlar einmitt að fjalla það hvernig stærðfræðin geti verið tækifæri til þess að efla mannréttindi. Og ég veit að sumir sem hér eru inni hlustuðu á Barbaru fyrir 3,5 ári þegar hún var einn af aðalfyrirlesurunum á ráðstefnu stærðfræði og stærðfræði örðugleika og hafa beðið spenntir eftir hún kæmi hérna. Barbara, it's a pleasure to have you here, and I know that some of the teachers that are here listened to you 3.5 years ago. They are waiting for hearing you talk, hearing you again. And so please, you can start telling us all about mathematics and human rights.
Hello everybody, can you hear me? So may I start by thanking the University and the Association of Teachers of Mathematics for inviting me to give this talk, which is a nice opportunity. And I'd like to thank you all very much for coming here this afternoon, since I expect you've all been working hard during the rest of the day. My title actually is taken from a small book that I produced a couple of years ago, and you can find a copy of that online, or you can get a copy from me if you'd like a hard copy. But I'm not going to be talking about everything that's in that book, but many of the things that I'm talking about are in there. So my title, Teaching Mathematics to Address Fundamental Human Rights. And you might ask, well, whose human rights are these? And I'm particularly thinking of the human rights of everybody in terms of learning and understanding mathematics. In particular, I'm going to be talking about inquiry and the use of inquiry approaches as part of teaching practice. So just a few words about the structure of the talk. I shall start from mathematics. Where else would I start? I'll move into dimensions of mathematical learning, and then that will bring me to the big and major question of what exactly does it mean to teach mathematics? And since I believe that many of you sitting there are actually teachers of mathematics, I'm sure you have your own answers to that question. So I hope you'll be thinking about those as I talk about what I see as being important, what it means to teach mathematics. In particular, I'm going to be talking about inquiry and the use of inquiry in the classroom, and I will have some examples related to that. And then, of course, importantly to this question of what it means to teach, I'll be addressing what are the roles of the teacher in working with inquiry in the classroom, and I shall have some examples of that. And then finally, I'll be addressing the question of how do we develop our teaching? So rather than the teaching being stagnant from year to year as we go through our practice, how does our teaching develop, or how can it develop? And I shall be drawing extensively on my own experience here as a classroom teacher some years ago, and as a teacher educator, and as a researcher in investigating the teaching and its development in mathematics. So, let's see if you agree with this. Mathematics is one of the most important subjects in the curriculum. It's central to so many areas of life and academic disciplines. Yet, students and people more widely struggle with mathematics possibly more than with any other subject. I wonder if that's true in Iceland as I perceive it to be true in other countries that I've worked in. Just to illustrate, I'm going to show you a very small piece of video. It's actually very old. It was captured by one of our UK television companies back in the 1970s when they took the microphone out into the street and they asked passers-by, how many 7p stamps can you buy for £1? A pound being 100 pence. Of course, nowadays, first-class stamps are 70p, so this was really some time ago. But let's have a look. Let's hear what people said.
£7 stamps could you get for £1?
7 stamps. So they sound like 9. How many what? Think about this one.
Got me, I'm sorry.
No joke.
No jokes.
7 stamps.
Of course, if you're put on the spot like that, it's very hard to think on your feet. I realize that. But in working that out, and presumably you can work it out and tell me how many 7p stamps it would be possible to buy for £1, you bring some kind of strategy, perhaps, to that working. It's not just that the answer just pops out, as it were. And so what strategy do you use and where does it come from? And different people might use different strategies. But the point that I'm illustrating here is that many people do find mathematics something very difficult to deal with in many situations, including those that they meet in everyday life, even though perhaps you don't meet such questions on the street every day. So here's my statement again about mathematics. And I would like to suggest that it's the right of every human being to know and understand mathematics relative to the context and purpose for which it's needed. This is not something special, it's a basic human right. And it begs a number of questions. In fact, I would say that these statements have profound implications for the teaching of mathematics. So, some important related questions. What does it mean to teach mathematics? What are the characteristics of good mathematics teaching? How does or can good teaching develop? I assume that those of you who are teachers here have very clear views on what good teaching actually involves, what it means to engage in good teaching. And perhaps most importantly, how can we teach mathematics for the effective learning of our students? Because they are the bottom line, aren't they? Why are we teaching otherwise if it's not to provide the best opportunities possible for our students' learning? Let's consider a particular student, Charlie. And Charlie was given a problem to solve. Let's see Charlie's problem and what he actually did with that problem.
109 And I'd like you to take away 70.
In this one, it's 0 from 9. You can't do that. So it's, you put 0 down. And it's 7, take 0. You can't do it, so just put 0 down again. And there's nothing to take from 1. So I think you just put 1 down.
Okay, Charlie.
So you've seen Charlie's solution to the problem that he was given. And you might have some comments on that solution, whether you think that Charlie was correct in his solution, whether you would have done the same, whether you would have done something different. Why do you think Charlie did what he did? Let's see what happened next.
Okay, Charlie. If you had £109 and you took £70 away, would you have that amount left?
No, that's what I realised.
Do you know in fact how much you would have left?
39.
Good boy. How did you work that out?
It's 70. It's 70, 80, 90, 100. Left 13, there's 9, so I've done 39.
You counted on from 70 till you got to 100.
Yes.
So in the first solution, you might have said, well, Charlie is wrong. Because if you take 70 from 109, you don't get 100. We relate it to mathematics that we know and to answers that we expect. So we might say, well, Charlie doesn't understand how to do subtraction. But in the second clip, you see that he clearly does. Within the context, he can work perfectly well. He can reason it, he can explain his reasoning. Did you notice him using his fingers to enable the counting in tens? So he's perfectly able to do the subtraction, and he can reason his way through it. So what went wrong in the first clip? Well, we might say, there might be many reasons, of course, but we might say that he was trying to apply some rule. And he hadn't quite got that rule sorted out. Maybe he was applying the rule incorrectly, maybe he had misremembered the rule, but it didn't give what we expect as being the right answer. But nevertheless, he can get the right answer. So there's a tension here, isn't there, between what Charlie was trying to do in the first clip and what he showed us he was able to do in the second clip. And I'll say it again because I think it's worth saying. It's the right of every human being to know and understand mathematics relative to the context and purpose for which it's needed. Maybe for Charlie, the context and purpose was not one in which you apply a formal mathematical algorithm. But maybe also we would want Charlie to have the flexibility to be able to use his own reasoning when that is the best thing to do in a particular circumstance. And how does a student like Charlie come to that recognition of which ways are most appropriate in certain circumstances? Perhaps he thought that when he was given the task by the interviewer that he was expected to use the formal method, and the formal method didn't work for him. This brings me to the question of what does it mean for students to learn mathematics? What might students reasonably expect to be offered in the learning environment? And I'd like to suggest 3 dimensions of learning mathematics. And maybe they're not just dimensions of learning mathematics, maybe they're dimensions of learning more generally. And I'm suggesting they are enjoyment, understanding, and proficiency. So enjoyment is about experiencing stimulating activity in interesting contexts, gaining inspiration and motivation from seeing the beauty of the subject, in this case, the beauty of mathematics. It includes affective factors, such as ease of access and comfort in engagement. Students should be able to enter readily into mathematical experiences and thinking and not feel threatened or excluded. Understanding involves insight into mathematical concepts and conceptual relationships, and an appreciation of mathematical activity and process that goes beyond the instrumental. By instrumental, I refer to rules without reasons, limited, short-term understanding, which depends on simple recall and lacks depth of structure or relationships to other mathematical ideas. And proficiency, of course, is important. It includes skill in being able to use mathematical rules and procedures, knowing when and how to apply these to problems, and being able to use mathematics in everyday lives, other disciplinary areas, and the world of work. I wonder if you agree. However, even if you do agree, I think we have to say that providing for these dimensions of learning is a seriously challenging task for any teacher. It's not easy. So what exactly does it mean to teach? I keep coming back to this question. Well, I draw on the words of a former colleague of mine, Professor Richard Pring at the University of Oxford. And Richard Pring wrote as follows: an action might be described as teaching if first, it aims to bring about learning; second, it takes account of where the learner is at; and third, it has regard for the nature of what has to be learned. He goes on to write, by a practice, for example, teaching, I mean a collection of different activities that are united in some common purpose, which embody certain values and make each of the component activities intelligible. I've emphasized the embody certain values. Mathematics is not valueless, and we need to be aware of the values that we're promoting as we teach. And again, he writes, for example, the teaching of a particular concept in mathematics can be understood only within a broader picture of what it means to think mathematically. So when you think mathematically, what does that mean? How do you think mathematically? And are you able to bring your students into those important ways of thinking mathematically? So that when they learn how to do subtraction, it's not an isolated skill that they learn, but it's something that's part of an important whole and is related to many other aspects of the subject. And moreover, Richard Pring writes, not attending to all of this is to accept a limited and impoverished understanding of teaching. Strong words. So, we might think about teaching for conceptual understanding in mathematics. Pring has talked about a worthwhile way of seeing the world, the moral judgment of a teacher over what is worth learning and what are worthwhile ways of pursuing it. And so we might ask, what is worthwhile in mathematics? We want to do mathematics, to use mathematics, and to apply mathematics. And in order to do that, we require mathematical understanding. I skipped over a slide, I'm sorry. I think this is important, so I'm going back to it. In addition to what Pring has said in my other quotations, he says, that teaching is a moral practice. Teaching is more than a set of specific actions in which a particular person is helped to learn this or that. It's an activity in which the teacher is sharing in a moral enterprise, namely the initiation of young people into a worthwhile way of seeing the world. There can be no avoidance of that essentially moral judgment of the teacher over what is worth learning and what are worthwhile ways of pursuing it. So we can ask what is worthwhile in mathematics. And I would suggest that that requires mathematical understanding, not just the instrumental type of understanding that you know how to use the subtraction algorithm, but a deeper understanding that relates different areas of mathematics, that enables us to apply and use the mathematics that we know. So the job of the teacher then, I would suggest, is to shift from mathematics to mathematical understanding, taking into account what it means to learn mathematics and designing the teaching of mathematics to enable that learning. So the teacher has to transform mathematical knowledge into opportunities for the learner to learn mathematics with understanding. In some parts of Europe, that's referred to as the didactics of mathematics. So you have a very challenging task, starting from the mathematics that you know and possibly love. You have to create opportunity for the students in your classroom to gain a mathematical understanding that they can relate to the world around them, to areas of science and technology, the world of work, whatever they're doing, and hopefully do it to enable their enjoyment of the process. Not much. How does or can the teacher do this? And how does or can this knowledge and skill develop? And I want to suggest that one way of approaching this is to bring inquiry into the classroom. I'm not saying this is the only way. I'm not saying that there aren't other ways that are possibly very effective, very useful alternatives, but this is just one way that I think we can address the dimensions of learning that I mentioned earlier. What do I mean by inquiry? Well, we ask questions and seek answers. We recognize problems and seek solutions. It involves wondering, imagining, exploring, investigating, reasoning, discussing, and overall looking critically at what we're doing. Why are we doing this? How do we do it and why do we do it? Who should be asking these questions? Well, I suggest that the students should. Maybe it starts off with the teacher asking these questions, but ultimately, if we're going to have inquiry in the classroom, then that has to involve the students taking part in this panorama of activity. And one way to get this going is to bring inquiry-based tasks, inquiry-based mathematical tasks to your classroom. Such tasks provide easy access to mathematical ideas. Everybody should be able to make a start. They provide opportunity to ask questions, solve problems, imagine, explore, investigate, and so on. They encourage discussion and reasoning, going in diverse directions, different levels of thinking, fluidity and flexibility, not just the one narrow right path to the solution. And they encourage student centrality and ownership in and of mathematics. And moreover, they should promote serious mathematical thinking. Yes, we're trying to create enjoyment. We want the pupils, the students, to enjoy what they're doing in mathematics lessons. But it's not just enjoyment for enjoyment's sake. It's not just having a nice, comfortable time together. There must be serious mathematics going on. So what kinds of tasks am I talking about? And I'm going to give some examples. As I go through some of these examples, I'd like you to be thinking about the 3 dimensions of learning. In what ways can the use of such tasks enable enjoyment, understanding, and proficiency? And moreover, how might you be using those as a teacher? What might you be asking your students to do in order to satisfy these 3 dimensions? So here are some examples of tasks. Here's the first one. Take any natural number and express it as a sum in as many ways as possible. So if the number we take is 10, we could say 2 plus 8, 3 plus 2 plus 2 plus 1, 1 plus 1 plus 1 plus 6, and other ways as well. Having written down the sums, multiply the numbers of any sum and find the largest product. So 2 plus 8, if we multiply 2 and 8, we get 16. 3, 2, 2, 2, 1, 3 2's are 6, 2's are 12, 2's are 24, 1's are 24, we get 24. 24 is bigger than 16. 1 times 1 times 1 times 1 times 6 is just 6. So in the 3 sums that I've written down, the largest product is 24. Is that the largest product we can get? Well, to find that out, perhaps we have to write down some more sums. Now, that's not too bad if the number is 10, but what if the number is 3010? Writing down all the sums would be pretty tedious. So this word here, this generalize, is very important. It's not just what is the case for 10, or 12, or 20, or 3010, or whatever it is. But can we generalize so that for any number, we could suggest what would give us the largest, which sum would give us the largest product? And to do that, we would have to investigate different numbers, we would have to try them out, we would have to look for patterns, we would have to make conjectures. It looks as if we take more 2s or 3s, we get a higher product. What is important in that? So making some conjecture and then trying to prove that conjecture. Here's a second example. You can see that in the first example, we're using number relationships. So in the process of engaging with A, students are working on relationships with numbers, perhaps reinforcing number bonds, reinforcing multiplication tables, all of those sorts of things, as well as thinking mathematically in the process of trying special cases and generalizing. In the second problem, you see we move into the area of probability. And in fact, questions of this sort arose because I and some colleagues were working with teachers in a project, and teachers said, we need some good problems relating to probability. How can we use inquiry within the topic of probability? So you can see here that this is a rather open problem. And in order to engage with that problem, you have to set some parameters. How many balls are in the bag? How many red ones, how many white ones? What does it mean for the least number of red balls to give a probability of drawing 2 in succession that's more than a third? What does it mean? Well, perhaps you start off and say, well, what if we've got a bag with just 1 ball in it? Well, that's no good, because if we've only got 1, we can't draw 2 in succession. So what if we've got 2 red balls? Well, if the bag has 2 red balls and we draw 2 in succession, then we're going to get 2 reds, because that's the only... So it's a certainty. So it's definitely more than a third. Good. We're starting to get somewhere. What if we put a white ball in there? And you can see that what I'm doing is building up in a sort of systematic way the possibilities that allow us to start thinking about this problem and addressing that problem, and ultimately to start looking for patterns within what we see. In order to do it, we've actually got to use some of our knowledge about probability in order to work out what the probabilities are in different circumstances. So the problem involves a lot of scope for inquiry, investigation, creative thinking, but at the same time, it allows students to practice ideas of probability. And my third problem here, this time in a geometric area, can you find any plane shape for which the area is numerically equal to its perimeter? Any plane shape, what are we talking about? Squares, rectangles, pentagons, hexagons? Where would we start? Well, can we find any square for which the area is numerically equal to its perimeter? And students, in my experience, very quickly come up with such a square. A 4x4 square has a perimeter of 16, it has an area of 16 square units. So they're numerically the same. Are there any other squares with that property? Are there any rectangles? What about other shapes? Triangles? Maybe that's a bit more difficult. Pentagons? Ooh, starts to be more difficult. And in exploring within this problem, students are addressing properties of plane shapes. They're exercising their mathematical thinking in trying special cases, looking for patterns, seeking to generalize, possibly offering conjectures and trying to prove them. Now, in all of these problems so far, I haven't said at what level of education I would be using that problem. And I think one of the important things about all three of those problems is that they can be used at a range of levels. So certainly I've used these problems, or teachers have used these problems with students at primary level, at secondary level, and at upper secondary level. And there's something more to be gained at all of those levels, even at university level, possibly. So one of the characteristics of a good problem is that it has this openness and flexibility to be used at different levels. I'm just going to illustrate the use of one of these problems with a piece of video. I worked in Norway for some years, and this is an extract from a Norwegian classroom in which the teacher is working with the students on the first of my three problems, on problem A. Perhaps you won't be able to understand the Norwegian, so don't worry too much about what they're saying, but have a look at how he's working with the students, what's being written on the board. It's about 4 minutes of video.
Okay, så er der mange måder, man kan lage realisationsstykker på mit liv. Nu har jeg et eksempel af det her.
1 plus 1
1 plus, okay. 1 plus 1 plus 1 er plus 8 for eksempel, det er jo. Så jeg ikke godt skulle være lettere. Jeg vil egentlig have til tid.
4 plus 4 plus 2.
Okay, 4 plus 4 plus 2. Nå tror jeg, alle her kan lage ganske mange forskellige typer addisjonsstykker i det tid. Men det som jeg oppdager, for hvis jeg ikke oppdager først, man kan endelig forstå det. Det er nemlig noe gøy nå, hvis man bytter ut plusstegnet, addisjonstegnet, med et gangetegn. Så skjer det noe litt interessant. Hvis vi ut et eller annet først, så tar jeg ikke det vi kommer på det. Skal man heller ikke bruke i dag. Det er kun hele tallet man skal bruke noe. 6 plus 4, så jeg ser en strek bort sånn. Så bytter jeg ut plusstegnet med et gangetegn. Hvor vi da svarer. Takk.
24.
24. Ok. Hvis vi gjør det samme der, hvor blir svaret da? Hvor 16, det er godt at gangetabellen er noen i orden. 9 ganger 1 er, hva sier det høyt?
9.
5 ganger 5 er
25.
Ja. Og 7 ganger 3 er
21.
Så har vi skrevet det på toppen nå. Nå har det 2 plus 2 plus 2 plus 2. Vi skriver på den. 2 ganger 2 ganger 2 ganger 2 ganger 2. Kan vi blive det? Anders? Ja, hvorfor så du trygt starte helt på det, så jeg kommer frem til. Anita?
32.
Det er jeg ikke enig i. 2 gange 2 er 4, gange 2 er 8, gange 2 er 16, gange 2 er 32. Ok. Det som jeg nemlig er ude etter nå. Nå skal du finne hvorfor et addisjonsstykke, altså det som står på den anden siden av streken, som vil gi størst svar hvis du setter inn et gangetegn i stedet for. For den som er størst nå, det er jo, ja, 9, det er i hvert fall ikke sånn, 9 pluss 1, det blir jo, det blir ikke bare det. 2 ganger 2 ganger 2 ganger 2 ganger 2, det blir jo 32, det var ganske høyt. 8 ganger 2 er 16. Nå må du sitte og prøve deg på en ark og lage forskjellige stykker som blir 10. Skal vi se hvor høyt svar du tar på. Det høyeste nå er 32, men jeg vet det er noe som blir enda høyere. Det som jeg ga dere nå, det er å prøve å finne det svaret som blir enda høyere. Så får vi med et mål her. Nå skal jeg prøve deg frem og se om du finner noe som blir større. Det er lov til å gjøre det sammen på grupper, eller kan gjøre det 1-1. Jeg synes jeg ser på nå at det er noe som ikke helt skjønt du skal gjøre for noe. Stemmer det, Mari? Du ser ut som veldig spørsmål. Du kjøpte nå. Men når du ikke skjønner det, så er det lurt å spørre nå. Ja,
Jeg skjønte det.
Det kan være noen på grupper, jeg kan hjelpe deg. Hvis du ikke skjønner, så kan jeg hjelpe deg. Alle som har skjønt det, får lov til å ta en blyant, et ark, og så er det i gang. Hvis du finner noen strand som er større, så må du komme og vise deg.
Introducing the problem, taking the students through, working through the problem with the number 10. Students were contributing, they were learning what the problem is about, and then finally he points out to them the highest number we got was 32. We used the number 10. What other numbers could we use? This is now for you to go away and explore. And the children went away and worked in small groups, working themselves further on that problem. Of course, that was just in one primary classroom. And if you think, could I have done something of this sort in my classroom, then you might have thought of setting it up in a very different way, particularly if you work at a different level with younger or older students. And one of the things that we tried to do within the project, where some of the people at the university, like myself, worked with teachers in a range of schools, was to emphasize the flexibility in problems, that a problem doesn't have to be only for students at a particular level. And we demonstrated this with one particular problem that we offered, which was stated, as you see here, how tall a mirror must you buy if you want to see your full vertical image? And my colleagues who designed this problem, of course they didn't invent it, it's a problem that's in the public domain, but they described how a teacher might use that problem at different levels. So they said, if you're a grade 1 teacher, this is what you might do. If you're a grade 2 teacher, you might do this. Or at grade 3, or grade 4. So what they're saying here is that we can take the simple statement of the problem, but think about how to interpret that problem for the particular students that we work with at our own level. And there might be similarities between levels, but as we move to higher levels, we might be making more demands on the students' reasoning, on what they're able to actually do in dexterity and so forth. And as you can see, they were able to write down something for all of the grade levels, so that a teacher at any grade level might be able to say, yes, I can see a way in which I might interpret that problem for effective use with my students. The teachers who were perhaps least persuadable about using inquiry-based tasks were our upper secondary teachers. And they said, we have a very well-defined curriculum, we have to get through it, it's important, the students have exams at the end of it, they have to be prepared to go on for higher education, we cannot take risks. And so there needed to be some persuading that there were inquiry-based tasks that would be valuable within the upper secondary curriculum. And so I have just a couple of examples here. So, give the function, as you see here, sketch the function on a pair of axes, and then find several equations. The equation of a line that crosses the curve where x is 1 and 2. The equation of a line of gradient 3 that crosses the curve twice. The equation of a line of gradient -3 that doesn't cross the curve. So there are here well-defined boundaries, but still there's an openness to what is being asked for. And students can work on this individually or in groups, they can compare results, they can look at a range of possibilities. If we then say, well, okay, we've worked with this now with a specific function, maybe we could work it with another specific function or another one, trying out different special cases. But what is the general case? If we now take a general quadratic, ax squared plus bx plus c, and ask similar questions, then what are the relationships between lines which do or do not cross the quadratic curve? How can we write down equations of such lines? How are the equations of such lines related to the particular quadratic function? And if we can do it for quadratics, can we go on and do it for cubics? And so in engaging with an inquiry-based question of this type, students are not only learning about how to interpret a quadratic function, how to find the roots of a quadratic equation, they're really seeing the idea of quadratic functions and linear functions being related to each other and how they can see the relationships. Moreover, if we use a package such as GeoGebra, I think some of you might be familiar with that as a very valuable investigative drawing package, then by using GeoGebra to generate functions so that we can actually see them and we can see the lines crossing and so on, and we can moreover change things very quickly so that we can see not only 1 or 2 or 3 functions, but we can get a picture more globally, then we can explore a situation that would be much more difficult if we were just working with a pen and paper in a traditional way. So one of the things that we were suggesting to the upper secondary teachers, not that everything has to be inquiry-based, but by designing inquiry-based questions and incorporating them in the normal topics of the curriculum, then students can start to have a more relational understanding of mathematics, a more conceptual understanding, rather than only working at an instrumental level when you learn how to do certain things, but you have really not much of a clue as to how they're all related to each other. Okay, so if you're using inquiry-based tasks, perhaps we're getting some sense of what the students might be doing, but what exactly is the teacher doing? Because perhaps working with students using tasks such as this requires a different way for the teacher to be interacting with the students. So, what is the teacher doing when students work on inquiry-based tasks? What is the teacher's role? Well, you might be circulating and listening. Certainly, in my experience, one of the most valuable things that a teacher can do is listen to the students. Because by listening to them, you get a sense of you get an understanding of what sense they are making of whatever the task is that you've set them. And then when you hear how they're talking about something, you can decide how best to interact with that. And of course, there are many ways of interacting. You might ask them questions which are designed perhaps to get them to consider things that they haven't considered already. Perhaps encouraging the students to ask their own questions. You know, they ask you something about what's going on there. Maybe they say, have we done the right thing? And rather than saying, yes, you have, or no, you haven't, then you can bring in other questions to try to open up the problem. If the students can work on these problems together, pairs, groups, even in the whole class, encouraging dialogue or debate, then that gives further opportunity, not only for you to listen to them, but for them to listen to each other. And perhaps really encouraging the students to listen to each other. Did you hear what she said? Do you agree with it? Could you say it in a different way? Enables that dialogue, which enables the whole group to actually talk mathematics, and through talking mathematics, to have a much better sense of understanding of what it's all about. We saw earlier in Charlie's case that when Charlie was asked about the context, suppose you had £109, he was able to reason his way through that. So he didn't only give the right answer, he was able to give the reasoning behind it. And it seems very important when we're working with students to actually foster that reasoning. So not only, yes, we've done the right thing, we've got the right answer, but how did we get it? What did we actually do to achieve that? And when you see that different people achieve in different ways, then students can start to see that there isn't necessarily just one right narrow way of getting to a particular point, but you can actually think about it in a number of ways. Students can then get confidence that it's actually okay for them to use their own reasoning, but not uncritically. They need to be saying, what is this about? Have I thought about everything that I need to think about? Are there other ways that I could have thought about it? So as the teacher, giving the students opportunities to reason and to engage in reasoning, and then to perhaps encourage debate and comparing and sharing of that reasoning. I think another important aspect of the teacher's role is prompting and challenging. Of course, in order to do that, you've got to have some comfort and security in the classroom situation. You've got to respect your students, and they've got to trust that they won't be put on the spot and made to look foolish, made to feel uncomfortable. So certainly prompting them and challenging their solutions. Have you thought about this? But what if this is the case? But within an environment in which people work together in respectful ways and trust each other. And setting up that kind of classroom atmosphere is not necessarily easy to do, but it's very important. A lot has been written, and a lot of people have thought a lot about how to work in these kinds of ways. And I point to just two areas of theory. John Mason, Leonie Burton, and Kay Stacey have written about the importance of the conjecturing atmosphere. So encouraging students to conjecture and test their conjectures, leading to generalization, abstraction, and proof in mathematics. I said earlier that it's important that there is some serious mathematics going on in this inquiry-based work. And part of this special nature of mathematics is its abstract nature and the ways in which we prove our assertions, sometimes in very formal ways. And we're doing students an injustice if we're not bringing them into these ways of working mathematically. So working with inquiry-based tasks encouraging the students to make their own conjectures and then think about proving those conjectures, introduces them to these more formal aspects of mathematics. The second area of theory comes from my own research, where I've observed teachers working in these ways in classrooms and characterized this in terms of something that I call the teaching triad. The teaching triad, as it suggests, has three main elements. The teacher's management of the learning environment, so designing the tasks, deciding how the students are going to work together, encouraging the respectful, trusting working relationships, and so on. And then within the management of learning, having a sensitivity towards the students. That is knowing your students. It seems to me very important, and I think most teachers probably agree, that knowing your students, both in terms of who they are as people and how they can work within a school environment, but also knowing what their mental capabilities are. Those who are very quick to take on to new ideas, those who need more patient encouragement, those who are more persevering. Having a sensitivity towards who your students are and their dispositions and needs is important to then engage with mathematical challenge. Because part of the nature of inquiry-based tasks is that they challenge the students to really get involved with mathematics. If the task is too easy, then it's just boring, and students might have a nice chat, but they don't really do much mathematics. If it's too hard and they can't engage, it's beyond them, then they probably just shrug and they don't do anything anyway. So we need to match the mathematical challenge to what we know about the students. And research in this area has suggested that effective teaching and learning in classrooms comes when there is harmony between sensitivity and challenge. So this gives a way of thinking about teaching and creating the classroom environment. So, with inquiry in mathematics, we see students engaging in mathematical tasks that are inquiry-based, which allows multiple directions of inquiry, specializing, generalizing, making and proving conjectures, multiple levels of motivation and possibilities for enjoyment. I've heard students say at the end of a lesson, "That was great, miss, I really enjoyed that." And they're not talking about just mucking around in the classroom. They're talking about the reasoning process and the debate that they've had in that. Differing degrees of challenge, mutual engagement and support, harmony in balancing sensitivity and challenge, and moreover, acceptance of and respect for difference. In any classroom, there are very wide differences in students' propensities, preferred ways of working, ability to achieve quickly, slowly, whatever. And I just have two examples here of teachers responding to students in different ways. The first one comes from an Open University videotape that I had a hand with many years ago. A teacher set her class the following task. If a number of circles intersect in a plane, how many regions can be created? She brought into the classroom a number of hula hoops. Do you remember hula hoops? And the students were throwing them on the floor, counting the regions, moving them around. Some people drew circles on paper, some people drew circles on the whiteboard. And the reasoning was something like this. If we have one circle, one region, two circles, we get 3 regions, 3 circles, we get 7 regions. Now, when you bring in the 4th one, how many regions? It becomes more difficult to count, so you count several times, and finally you decide 4 circles have 13 regions. But what happens when we bring in the 5th one, or the 6th or the 7th? How long can we go on counting regions? At some point we have to start reasoning. And one way of reasoning, perhaps, is to draw up a table of values and start looking for relationships between the numbers that we're generating. It may be possible then to conjecture what the relationship might be if we have 10 regions or 50 regions or so on. But then how does that conjecture relate to what is actually going on when we bring in the next, how many regions are being cut, for example, when we bring in the next circle? And maybe that gives an insight into how we can actually prove a conjecture. But one girl, at least in the classroom, was doing something different. And Mary had arranged her circles like this, which was rather different from what some of the other students had been doing. And she brought it to the teacher. She'd got a table of values, and the teacher discussed with her what she was finding from this investigation. And they talked about how she was generating her table, what patterns she could see in the table, how she might generalize it. And then finally the teacher said, "You're doing something different from everybody else, Mary. Don't worry, that's fine. Just ignore what everybody else is doing." So she didn't say, "Well, Mary, perhaps now you ought to go and look what these people are doing, or perhaps you ought to do it in this way." She was respecting and making a decision. Maybe for some other students, she would say, "Go and have a look at what they're doing over there." But her decision here was to value Mary's work. And I suggest here that opportunity for all allows one to be different. This is something that I observed myself in the classroom. If you look at that figure, ask yourself, what is it? What shape is it? I wonder what you would say. I saw a teacher offer this and ask this question to a class of 12-year-olds. He asked them to name the shape, which he'd drawn on the board. And one of the students said it was a trapezium. Many of the students agreed. Hands had been up, hands went down, they thought it was a trapezium, but not everybody. And the teacher said, "If you think it's not a trapezium, then what is it?" And one student, Michael, said tentatively, "It's a square." And there were murmurings, giggles, "A square?" And Michael went on, "Sort of flat." And the teacher looked puzzled. I think the teacher couldn't see a square either. So he invited Michael to come out to the board and explain the square. So Michael did. He indicated that you had to be looking down on the square as if it were your book, only tilted. And he moved his hands to illustrate that. And then the teacher said, "Oh, I think I see what you mean. Does anybody else see what he means?" And there were murmurings, puzzled looks, tentative nods. And then the teacher drew onto the board this. "Oh, yes," said the students, and there were nods around the class. Now, what the teacher was doing there, the teacher had not intended to draw a square. He'd drawn a trapezium. They were going to talk about trapeziums. But the teacher was able to respond in the moment to what Michael offered, not to say, "No, that's a silly suggestion, it's clearly not a square," but really to listen to what Michael had to say about it, and then value Michael's response, and moreover, show the rest of the class that there was another way of looking at this, and it was valuable because it took them into 3 dimensions. And in fact, we have some discussion of this in the research. Roland and colleagues talk about this being contingency, when the teacher doesn't follow the path that has been planned, but branches out in recognition of a valuable opportunity from something that arises in the lesson. So, inquiry in mathematics teaching can involve teachers as inquirers, exploring the kinds of tasks that engage students and promote mathematical inquiry. Ways of organising the classroom that enable inquiry activity with all its attributes. The many issues and tensions that arise related to the classroom, school, parents, educational system, society and politics. We work in a real world. We can't isolate the classroom from that world. And reflecting back on what occurs in the classroom with feedback to future action. So not only doing inquiry in the classroom, but exploring how to work with inquiry in ways that lead to good learning for the pupils. And we might see an inquiry cycle of activity where we plan, we act and observe, we reflect and analyse, and we feed back for future planning. So design a task, use the task and observe what happens, perhaps gather some data from that, reflect on what occurred, analyse the data, and use what has been learned through observation and analysis to redesign the task. I'm talking about the teacher getting engaged in a research process, because as a result of such engagement, you generate new knowledge. You come to know more about what you're doing and why you're doing it. And some people call this action research or design research. I'm talking about inquiry in two layers. Inquiry in students' mathematical activity in the classroom, and inquiry in teachers' exploration of classroom approaches. And the second one of these leads to more knowledge and more expertise in the first. However, it's very difficult for teachers to engage by themselves in inquiry or research processes. If you're engaging in inquiry in the classroom with your students, and you want to engage in inquiry into your teaching, then rather than just doing that on your own, you might get in touch with somebody at your local college or university. I've worked extensively with teachers who've been interested in working in these ways, and it's a delight, I would say, for people like me to have the opportunity to work with teachers who are really thinking about how to develop and improve their teaching. So you might want to get in touch with local teacher educators who could work with you in this way. So I'm suggesting teachers and educators in collaboration. Teachers as inquirers into what works for their pupils in the classroom, educators as inquirers into what works for teachers in developing teaching, and there can be a very effective synergy when they do research of this kind together. So I invite you to think further about using inquiry processes and indeed inquiring into your own teaching, perhaps in partnerships with people like myself, and really getting a lot of satisfaction and knowledge from the process. Thank you for listening.
So, Barbara, thank you very much for this enlightening lecture. If anybody would like to ask Barbara about something related to her talk, we have a few minutes that we can spare, and you are, if you don't want to speak in English, you can ask in Icelandic, and we can help you with translating it. Any burning question? I had one question for you, Barbara, but you answered it on your final slide. So my question to you was exactly what teachers that are not used to deal with mathematics in an inquiry-based way themselves and would like to do that with their students, if you could give them some advice. And yeah, would you like to add something to that? You have already answered it.
Well, let me introduce you to my good friend and colleague Jónína, who works at the University of Iceland, and who I'm sure, together with some of her colleagues, would be willing to discuss this with you. But may I say that we have quite a broad literature in the areas of teaching mathematics through inquiry processes. I don't know if the Teachers Association in Iceland has such publications. Maybe you do in Icelandic. In England, we have an association of teachers of mathematics who produce some very, very nice materials that can be helpful in making suggestions, tasks that you can use, suggestions for ways of working at different levels. And I mean, if you go to the web page of the British Association of Teachers of Mathematics, you will find a wide range of possibilities there. I would recommend very strongly teachers who are interested starting to work together, because it's really good to have other people to share with, to stimulate ideas, to feel that you're doing and achieving something jointly. So the literature, the working with your colleagues for sharing an inspiration, and working with colleagues in the university who would be very willing and interested to work with you in developing teaching.
Thank you, Barbara. I would like to add that this talk was recorded and will be available at Menntavísindasvið within probably a few days or weeks, and we will send you a mail to let you know when it's available there, and you can then encourage your colleagues that couldn't be here today to look at it. Takk ykkur kærlega fyrir að koma og á þessum tíma. Ég veit að það er mikið að gera hjá okkur í skólanum og vona að þið hafa haft gagn af þessu, og ég hvet ykkur til þess að bregðast við því sem að Barbara talaði og einmitt líka að skrifa þá það og birta í flatamálum sem þá okkar tímarit. Guðný, þú vil...
Mér datt bara í huga að það væri hægt að tala saman á fésbókarsíðu Flatar. Það ekki ein leið? Já, við erum náttúrulega að reyna að vinna á að koma Strærðfræðitorgin á Menntavísindasvið og það er svona verkefni sem í vonandi fer að fæðast, gerast eitthvað í því.
Já, þetta var held ég bara góður endir á þessu og þakka ykkur aftur fyrir, og við munum vinna saman að því að það ekki að standa að því að stofna Strærðfræðitorg á Menntavísindasvið. Þá verður þessi fyrirlestur væntanlega birtur á því torgi, en fram að þeim tíma verður hann væntanlega inn á Menntavísindasviðinu. Og þakka ykkur aftur fyrir að koma.